The broadcast is now starting. All attendees are in listen-only mode.
Hello, and thank you again for joining us for this week's Ask Joe webinar series. Today's topic is going to be on site calibrations using Survey Pro. This is a question that comes up quite often, being on the sales and support side with Spectra Precision and having been with TDS prior. This has always been a topic that comes up quite often. I'll leave it at that. So joining Joe today will be Graham Briggs. Graham is a geomatics engineer, and he was very instrumental in the development of Survey Pro's calibration routines. So he's going to join Joe Sass with the presentation today. So a little background on Joe Sass as well. He's our channel development manager and as a liaison between field application engineer for product marketing, sales, and engineering. With his degree in geography, it blends nicely with his passion for surveying. Since 1998, he's been active in the California Land Surveyors Association, and in 2004, he began representing us with the RTCM Standards Organization and currently sits on the board of that organization. So with that, I'm going to turn it over to Mr. Sass, and again, thank you for joining.
Thank you, Joe Binder. Appreciate that introduction. It makes me sound better than I am. When I was asked to do this presentation, I quickly figured out that I was in over my head, and so I enlisted the help of Graham Briggs, and he graciously agreed. So if I go astray on this presentation, he will correct us, and he is the authority on this topic that I'm going to be talking about today. So, find out how to advance my slide. What is a site calibration? And basically, in terms mostly of GNSS we're talking about today. We're trying to take these signals from space and manipulate them into something that we can use. I use the example of an apple in its native format, and we have to do some manipulations to get it to apple juice so we can drink it. And that's really kind of the same effect that we need to do when we're taking latitudes and longitudes from space and trying to convert them to northings and eastings on the ground. So when you start a GNSS survey, and what I mean is that you've got a GNSS instrument connected and you are opening a job and you want to start the survey, you hit the Start Survey button. Survey Pro will prompt you with this screen. Are you going to work on the ground with ground-based scaled distances or on a mapping plane which has grid distances that very well are different than the ground distances? So we try and walk you down a path that helps you stay out of trouble, though you can get in trouble if you force the system. We'll talk about geoids later. Geoid is the vertical element of GNSS, and Survey Pro is supporting the latest geoid model in the United States and around the world, I would imagine, as well. You can input mapping plane definitions. We cover hundreds and hundreds of mapping planes throughout the United States and the world. But if you want to key in your own custom definition, we can certainly manage that as well. When you use a mapping plane, it's always associated with a datum. And again, we have hundreds of datums to choose from within our coordinate system library, which is the same as Trimble uses their .csd coordinate system library. Graham will talk about this later, but whatever you're doing, regardless, when you're using GNSS, even if you have good vertical control, it's not a bad idea to have a geoid model attached. Never does any harm, unless you're using a different geoid model than the previous time. And again, Graham, feel free to jump in here if I go astray. When you're doing RTK and you get corrections from your base station, you really don't know what datum that base station is on. And so when you get a fixed or a float solution, as you see in this example, the coordinate basis, the POB, the initial datum is going to be defined by my base station. So is my job properly oriented to the base station coordinates or not? Usually not, is my experience. So Survey Pro uses the base station broadcast position to set the initial datum. That's what you're going to get when you get a float or a fixed position. It's going to be based on the datum of the base station. And if there happens to be northings and eastings in the point file that are available for this base station, that can be used as one of the site calibration points. You see also that we have a lot of these messages that pop up in Survey Pro, and you can turn it off. I find them to be helpful. I don't find them to be inconvenient, but if they are, you can turn them off, and there is a reset button in the job settings menu dialog. The idea of a site calibration is basically this idea of point pairs. You have a northing, easting elevation, and you combine that with a latitude, longitude, height. We call that a point pair. And when we're pairing these inside Survey Pro, Survey Pro likes to take the point number and add an underscored GNSS to indicate that this is being used as a point pair with point number 1. You don't have to abide by this nomenclature. You can certainly change it. You see those fields are typable, but it is a convenient syntax, and that's the way Survey Pro pairs them together. There is a special situation that I point out here, where if you happen to have a single point in the job, and that job is on, the base station is on that single point, Survey Pro presents this screen to you here, where you can just do a 1-point calibration at the base, and you're often going with ground-based distances oriented geodetic north.
And maybe just to chime in here on that topic, Joe, you know, the equivalent setup that you get here is, imagine if you put a total station on the ground, plunked a nail in the ground, you know, gave it whatever coordinate you like to begin, say 5,000, 5,100, and then you did an old-fashioned sunshot establishing a geodetic azimuth of that station. That's essentially what you get in this special scenario of a 1-point calibration. And it's only offered to you as a choice when you have 1 point in the job, because we know at that point you're setting up a new job and the orientation of the job is kind of arbitrary, so we can use true geodetic north. As we'll discuss further in the presentation, in the scenario where you have multiple points already in the job and you need to fit to those, that's where we'll be showing you the multi-point calibration, which is the usual case.
And that would be the top choice, occupy control. So here you can see in this example that I've used that we've got a vertical horizontal control point number 1 with a 5,000, 5,100 position, and we've done that point pairing, that 1-point calibration, created 1 underscore GNSS, and even though it was shot with the latitude and the longitude, we've reconciled it to this 5,000, 5,000 system. The site calibrations, I hate to read this to you, but you can see that I've highlighted the projection tab. This setting is only available, this menu choice is only available when you're in a GNSS mode. As seen on the far right, you can see the GNSS icon. You can get into some of these parameters if you're in a total station mode through the job settings scale, but I would not recommend that. You can see here, if I go into that projection tab, that there are, the calibration has been solved, that 1-point calibration has been solved, and I can see details of it by pressing on the show details. If instead I click on the solve calibration, I'm taken to this page where I have the ability to add additional points to my calibration. This thing that is called Blunder Detection, that is a unique feature of Survey Pro that was reasoned out many years ago and engineered into the software. You cannot call an inch a mile like you can in other softwares. It will detect. The show details button here actually provides more details about the calibration, where you can actually see the parts per million and the scaling factor. The scaling factor should always be 1 followed by a bunch of zeros, or a decimal followed by at least 4 nines. Otherwise, you've got some problems probably going on there. This is the actual data collection page where I'm going to start solving a multi-point calibration. You can see that Survey Pro is looking for a local point, so I can choose that from my list of points. I can choose it from the map. I can create a new point right here. I can choose whether or not this point will be held vertically, horizontally, or both. And once I'm leveled up on the point, I've defined the point field, the local point value that I'm going to be calibrating to. I would then hit the Start Control Point Occupy button, and that would initialize the raw data or the RTK data collection. You can see that in I just show you this to illustrate that there are really three types of coordinates. We have what's broadcast from space, the so-called WGS84, but what we're really interested in is that grid coordinate, the northing, easting, and height, or elevation that we're going to be surveying or staking out. This is the GNSS status page. So I kind of say the reverse here of what I should say. If this box is deselected, that would be typical of a total station setup. In this case, I've selected a state plane coordinate system, and the scale factor and the rotation will be defined by the parameters of the state plane coordinate system. Notice even if I've got other vertical control out there, I'm going to attach the Geoid model because it's never a bad idea. If the control points are on a grid system, and this is typical of institutional type projects, maybe corridor projects by a DOT or water projects by a water utility. A lot of times their plans, their whole system is based on grid coordinates. And this is something that we run into a lot. How do I localize? Do I just treat this grid system as if it's on the ground and just localize to the local control? The answer is no, you don't. If I'm in North Carolina and my grid system is North Carolina, then I should choose North Carolina because it's a specific type of projection for this area that's being used on the ground. So this brings up a point that Graham really wanted to speak to, and that is calibrating to a grid system. How do you take your datum that's being provided from the RTK base station, and how do you calibrate to a grid, and how do you, more importantly probably, how do you not calibrate to a grid? So I'll let Graham speak to this.
Yeah, thanks, Joe. I really just wanted to re-emphasize this point because it can be very important. And we do hear a number of times from users in the field where they'll say, you know, hey, I always choose the ground calibration, or some people call it no projection, no datum. I always choose the no projection, no datum mode no matter what. And then I just calibrate locally and I get a pretty good answer. And that is true. You will get a pretty good answer, especially if your site is no more than half a mile across, or, you know, 1.5 kilometers across. If, however, your site starts to get larger, you will actually get a bad answer. And the reason is there's a mapping plane involved in these calibrations somewhere, and mapping planes have a particular shape. So if you don't have a projection or a datum, of course, you only have one choice, and that is to use the ground calibration mode to calibrate on some arbitrary coordinates. And that's typical in the example where you had a total station survey from years ago, or somebody did something not connected to a geodetic datum and they just have a bunch of coordinates. That's your only choice, and that's the appropriate choice there. But as Joe emphasized, if you know that your coordinates on the ground that you're trying to match to, maybe they're DOT's monuments, maybe they're NGS monuments, if those coordinates are given in a specific mapping plane, it is very important that you choose that mapping plane. You can still calibrate to those coordinates. You know, the nature of the adjustment will just be proper in that case. And the reason it's important to choose the right mode is because different types of map projections have different shapes. So go ahead to the next slide, Joe, and I'll try to show you a picture of really what that means. So here we have 3 different plots, right? So these 3 different graphs of these surfaces, this is actually a plot of the scale factor over a particular area, and this area is in Southern Oregon, where I was doing some testing and analysis with one of our customers because they were having this exact same problem. They had a large site, you know, 10 kilometers across. The grid coordinates, or the control coordinates, pardon me, were given in Oregon South State Plane System, and they were choosing default ground mode to calibrate on. And they were seeing errors in the neighborhood of about 3 centimeters or 1.5 inches across this 10-kilometer zone. And then they were suspicious about that because that's a little bit outside what the precision that they expected. And the problem is that every different map projection has a different shape. So the map projection you see on the left, that's the oblique stereographic projection, which is the projection we use in the background by default anytime you choose one of those ground calibration scenarios. The projection in the middle is the Oregon South State Plain Zone, and it's a Lambert projection. And you notice right away that they have a different shape. The stereographic projection looks kind of like a bowl, while the Lambert projection looks more like a half pipe with the pipe running east-west. And then finally, the final picture on the right-hand side is an example of a transverse Mercator projection. It's at a slightly different scale, which is why it's lower, but what's important here about it is the shape. You notice the Mercator projection looks like a half pipe with the pipe running north-south. I like to equate things to the real world, so I like to talk about this effect as the so-called grain of the map projection, right? If you do any woodworking or work with materials like that, you know that often materials have a grain, and you don't want to go against the grain of the material. If you're using a Lambert projection, the grain of the material is going east-west. If you're using a Mercator projection, the grain is going north-south. The reason we choose the oblique stereographic projection for our default calibration is because the scale distortion is kind of spread evenly in all directions, like you would get in a total station survey on flat Earth. The important thing to remember here is that a calibration is a best fit, where you're trying to scale and rotate one surface to another. If those surfaces don't have the same shape or the same grain, then you will introduce errors. And in the case of the customer we were dealing with in Southern Oregon, he actually found that his control points that were north or south of the middle, they closed very well. Because as you can see, if you tried to fit the bowl into the half pipe, across the curvature of the pipe, it would work great. But as he was going east-west is where his control points were no longer fitting. And that was just a real-world example of why it's very important to pick the right mode. If you have no projection, no datum, pick the ground calibration mode, and you'll get that best approximation for flat Earth. If you have state plane control coordinates or some other known mapping plane conformal coordinates, it's very important that you pick that type of mapping plane to calibrate to.
Okay, so I want to illustrate this example in the following. The point here that you see that's called base was a submission that I sent to Opus, and it's the coordinate system I consider to be the coordinate system of the country. And yet when I get corrections from a nearby base station, I have this delta. There's a 10 centimeter difference or an 8 centimeter difference between these two, and I need to reconcile them. Now, the Opus solution, you can see here that I'm in California State Plane Zone 6, and I still have the opportunity to solve this calibration between these 2 points. Because I'm in a grid system, California State Plane Zone 6, I don't need to worry about rotation or scale. It will be solved by my location. So I can do this with a single point, even though more points are always better, I would say. So I go in there and I say this base equals GNSS base, and that's how I connected them. Now Survey Pro is warning me there's too few points to check horizontal, too few points to check the vertical precision. Absolutely right. That's why I say check shots are always a good idea. And you can always, as the customer probably did there in Southern Oregon, go and add additional points. The point being that you're using the correct projection method. As you can see, they are different shapes. So here you can see that using the single point, the one solved by Opus versus the one that I got as a result of corrections from a local core station, and I've solved it. It's a simple translation in this regard. And with that in mind, you would say, so I can use the translation routine. We'll talk about that. It's always a good idea to check other places to make sure that you actually did do the translation correctly. But 1 point theoretically is sufficient. And you can see here, I've gone into the Survey Pro COGO routine, and I've surveyed from that, I've inversed from that point base to base underscore GNSS, and you can see they are exactly on top of each other. So if your control points, as Graham mentioned, are based on ground distances, and that's typically, jobs that are based on total station type measurements, you need to localize on the points. And then the scale is therefore computed by the points that you calibrate to. And scale can be confusing. You really have two different scale factors which create a third scale factor, right? You have projection scale and elevation scale, and those two combined together will multiplied together will give you the combined scale factor. You can see, as I mentioned earlier, a bunch of nines. In this case, a bunch of nines are the scale factors, and that's what you want to see, or one with a bunch of zeros after it, depending upon your location within that projected system. That's what determines the scale factor. Where am I at? Am I dead center? A lot of times, dead center in a transverse Mercator is 0.99996. And as you go out, it increases until you get to some ellipse, oval shape, and then it starts being greater than 1. This is so unusual to come into this place. This is in a total station mode, and I have the ability to set up scale, and I can get in a lot of trouble. I better really have good purpose to enter this page and really understand what I'm doing, and probably have someone check my work or check points on the ground to make sure it's working. I have seen jobs where the entire thing is set up in grid, and when you take your total station out there, for instance, you need to change the scale factor to match the project site. That would probably be an appropriate time to come into this page.
Yeah, and just to elaborate there too, Joe, and because you use the word automagic here, which I think is appropriate. If you don't touch the defaults, Survey Pro will take care of scaling for you anytime you're using a mapping plane from the coordinate system database. Of course, if you're in ground calibration mode, that's assuming that you just put your total station on the ground, you've got a scale factor of 1, and it works in that space. What we're talking about here is when I have to choose a specific mapping plane, and I know there's some grid scale and there's some elevation scale involved, the default behavior of Survey Pro is to calculate the proper grid scale factor for each setup and the proper elevation scale adjustment for each and every shot or observation from that setup. So you will automatically always get things properly scaled. So as Joe said, it's unusual to come in here because if you just pick the mapping plane, it will automatically set up this mode for you. Typically, you only want to come in here when you need to do something different than the normal proper way to scale, which does happen sometimes. For example, some cities or some jurisdictions, they've taken the scale factor for their county or for their jurisdiction and they've calculated an average and they say everybody use this one scale factor. So you can come in here and override the automatic setup by setup specific scale factor to use a prescribed scale factor. And that's maybe one of the more common reasons you would come to these scale settings, because by default, we'll do everything properly for you.
Thank you, Graham. You can fix things here, but obviously with the red X, we're saying it's better to work really with the coordinate system, the datum, and to work at that level versus taking a bad location and just correcting it through the translator, correcting it through the rotate. You can do this, but it's not a best practice, shall we say. There are times when you just need to slam it out and get it done and you don't care, and that might be a financial consideration or some accuracy budget that you're allowed to be able to just kind of make it work. But we would encourage you instead to go into the projection parameter, the projection page, and work with these issues through that interface. That's its intent.
Yeah, and really the gist of that is that when you take an observation, Survey Pro stores that observation as a vector and can recalculate the coordinates based on the original observation. So for example, if you add more calibration control points and resolve the calibration, all of your observations will be readjusted, or all of your coordinates, pardon me, will be readjusted from their original observations. The moment you use the adjust menu and you take something that was observed and scale it or translate it or rotate it, manually with the adjust menu, we have to kind of sever the connection to the original observation, and we turn that thing into, a regular store point that is no longer connected to observation. So anytime you do an adjustment, you sever your ability to fix rod heights or to recalibrate with additional control points. You've essentially, recalculated that coordinate, and we turn it into a store point, and it's no longer connected to the observations. And that's really the important reason why it's not recommended to, it's always recommended to, do the recalibration or do the adjustment based on the original measurement coordinates, and understanding that using the translate, scale, or rotate from the adjust menu will sever that connection to the observation.
Thank you. We call that dependencies, point dependencies, and that's the term we use inside Survey Pro to keep all of the data connected together. Again, I've showed this page before. I think this is probably the third time this page has been brought up onto the screen. Survey Pro is going to ask you, do you want a ground calibration or a mapping plane? And this introduces sub-questions to both of these, correct? I mean, if it's a mapping plane, we need to choose it. If it's a ground calibration, we need to define it. And so I'm going to work you through these two choices in a flowchart kind of way. I don't want it to get bogged down, but it is textual in effort. So the previous page, do we want to work, on the ground, or do we want to work in a mapping plane? And that's the same thing. We're aiming to get to those green boxes at the bottom that say ready to survey, right? And if we're optical and we've got ground coordinates, we can just occupy backsite, we're ready to survey. With GNSS on the ground, we're going to have to calibrate to that ground. We're going to have to go out there and occupy, and we're going to have to do some type of a calibration to make it fit from space into our project. Mapping plane, again, we just need to select the coordinate system. You notice here just what Graham just said. I can use a mapping plane coordinate system with the total station, and Survey Pro will manage the scale factor for me. I don't need to additionally go in there and set a scale factor. The state plane coordinates that I provide into the total station will define that scale factor for me. So let's break it down a bit further. We select our coordinate system. Okay, that's great, but is the base on a known point or an unknown point? And you see here we use the difference between site calibration may be performed and must be performed. So on a known base, we could go out there and just start surveying, but we might want to check our work and make sure that it truly is where it says it is, and we can provide we can perform the site calibration if we want. In either instance, on the right, though, we must perform the calibration to be in a position that we're ready to survey.
And I think a real world example on that one that's kind of simple to understand is, so on the left-hand side, so let's say the scenario is, like you mentioned, Joe, you got a DOT that's doing a corridor project, and 5 years ago, they put a bunch of iron in the ground and established control coordinates based on a good solution from the VRS, NTRIP provider. And then they're holding those coordinates throughout the life cycle of the project, which might be several years. Well, a couple of years ago, that NTRIP provider, they readjusted all their coordinates. So now they're just a centimeter or half a centimeter different here and there. In that scenario, you will probably want to do your calibration to do that little tiny, an inch or two adjustment from what the NTRIP broadcaster is now broadcasting today versus how that fit a few years ago on the control coordinates that are still being held, right? In the second example, that's very much like a resection scenario. Hey, I put my instrument somewhere that is unknown, so I must hit some control in order to get close. And in that case, you'd be looking at like a 5 to 10 meter adjustment, because that's the precision of a standalone GPS base when you just set your own base on a new point.
So another way of saying what Graham said in the inverse is that the reason you may perform a site calibration with the known base is because the known base may truly be unknown. And that couple of centimeters of difference turns that known base into an unknown base. And then we're on the other side where we must perform the calibration. I would say the known base is one that we've used every day for the past 2 weeks. If we're in an unknown projection and datum, we're either going to have control or we're not going to have control. If we have local control, we're either going to set up on it or we're not. A lot of times the control points for GNSS are in the middle of the street, and it's not very convenient to set up a base station in the middle of the street. You'd rather have it in that empty field off to the side that has no traffic of cars or people, right? So you would set it up on a point of convenience, and then you would collect at least 2 control points. 2 control points will give you scale and rotation, which is the absolute minimum. And then you can add control points as you want and do a multi-point calibration throughout the day. If you're just going to assume a first point, we showed you that special situation where that base is set up on the assumed point. You can just call that the single point calibration. You're ready to survey, or you can do that single point calibration with your rover and get ready to survey.
And one quick comment here, Joe, as you mentioned, I want to stress that when you get started, 2 points is a minimum. Survey Pro will prompt you to collect at least a third so you can check your work before you move on to do data collection, but that's not mandatory. You can always start with a valid coordinate system after 2. As Joe said, though, you can do some data collection and then add more points throughout the day to improve your calibration. And when you hit resolve, all of the coordinates will readjust again because everything's connected back to the measurements. I did want to point out one important thing, though, is that if that is true, of course, for data collection where we can just readjust coordinates. But if you've done stakeout and then you add more points and resolve the calibration to get a better solution, of course, we can't magically go back and move the iron that you placed in the ground, right? So if your intention is to do stakeout, it's always a good idea to collect all of your calibration control points that you're going to be using, adjust them, check them before you actually start putting anything in the ground. Because if you readjust the coordinate system, then that's going to move the final solution of where your as-built was versus where you actually put it in the ground at the time. So we can't go back and move stakes. If you're doing stakeout, finish the calibration before you get to that stage.
Let me just pile on to you, Graham, and ask a question I don't know the answer to. But if I have done some stakeout, I get a results page, and that results shows the final northing and eastings and heights of the point that I just staked. Are you saying that if I then later go and add more points to my calibration, that the results page will change?
No, actually the results are the results, and we kind of locked that down in the stakeout context at the moment that the results are stored. Now, if you stored a stakeout point and then went and did anything that changed, whether that's added more calibration points and resolved the calibration, or it could be changed a rod height in the edit raw data and readjusted the survey. It could be a number of things that potentially change the current coordinate for a point you had previously staked out. And when that happens, if you look through the raw data view, you will actually see a warning that tells you that what was reported as the as-built location when you staked it is now different from the current location. But for all cut sheets and all reporting of what the stakeout delta was, that is locked in and hard-coded at the time that you store the stakeout point. Again, you might do something, you might change a rod height, or you might recalibrate with additional control points that changes the current solution of that point coordinate in the survey, but the stakeout report will always show what was shown at stakeout time, and you'll receive a warning. That point will kind of be flagged, and it'll say, hey, this stakeout point is no longer where it was when the stakeout happened.
Just emphasizing the point, we should get the calibration completed before we do any stakeout.
Any stakeout, exactly. But if you're just doing data collection, you can put in 2 calibration points, get started, collect 1,000 points, and then add a third and a fourth calibration point. When you hit solve after that, each and every subsequent calibration point will readjust all measurements.
Beautiful. Okay, so I mentioned it earlier that there are really 3 types of coordinates. You have the global stuff coming from space. Let's call that global, WGS84 if you want. But we localize that, as you can see, to the current standard, which is NAD83, and those would be called local latitude, longitude, height. NAD83 is directly tied to a geodetic value. And then you can see we take those latitude, longitude, heights, and we convert those into some type of a northing, easting, and an elevation, as you can see throughout the country there. To do that, we apply a datum. So we take those global coordinates and we apply NAD 83 to get the local latitude, longitude, height. And then on that local latitude, longitude, height, we apply a map projection. Probably can't see it, but the map of the United States there is a pictorial representation of the type of state plane coordinates they have. If I were to choose one example, you can see Wisconsin has 3 zones. They're Lambert zones. You've got a north, a center, and a south. And that's the way their state plane coordinates are. Generally, state plane systems are developed based on the geography, the shape of the state. So you can automatically know that a state like Tennessee is going to have a Lambert parallel because it's a long, skinny state. So we do handle the elevation separately. GPS has no knowledge of gravity, and yet gravity affects our elevations. We're still understanding that. We're still learning more and more about gravity, but we call this the geoid or the geoid separation. And at some point in the geodetic realm, we pull out the height part of the latitude longitude and treat that separately, usually through the use of a geoid, though not always. So, site calibration example, we have our data from space. We apply a datum to get our local NAD 83 in my example. We pull out the elevation and apply a map projection. But when we get those corrections from our local cores, we get a northing and an easting based on our map projection. We get an elevation based on our geoid, but it doesn't match my control in the street right in front of me. So I then do a horizontal and or vertical calibration to actually get to my destination datum. So if you do the math there, you're looking at like 14 or 15 parameters of transformation that actually needs to occur to get to your target coordinate system or datum.
And as we mentioned before, that's either a large gross adjustment because you started from an autonomous position, or maybe it's just a small adjustment because you're tweaking, somebody's N-trip network to somebody else's realization of what's supposed to be the same datum on the ground, but when they actually pounded the pins in the ground, it might be a little bit offset.
So some of you may know Phil Stevenson. He's retired, living in Oklahoma. He was my mentor for many years, and I respect him a lot. And he had this expression, the proof is in the dirt. You can see a big pile of dirt. You can have all the calibrations, all the theoretical knowledge, all the parameters, what type of projection, the scale factor, but until you actually go out there with the prism pole and put that tip of that prism pole on a point on the ground or several points on the ground, you really don't know that you're on datum. And that's what he meant by saying the proof is in the dirt. You have to go out there and do it and make sure you are on datum. So I walked through this example, I walked through this example that many of you have probably seen before. So if I just hold one point on my project, Survey Pro will allow me to do that. It will give me a scale factor of 1, and it will assume a geodetic or a spin axis north as far as the Earth is concerned. And that becomes my coordinate system, and I can go to town with that, and I can then develop other control based on this arbitrary single point. If I add a second point, I've now introduced scale and rotation. I don't know if either of those are right because it's a perfect fit. I used the expression an inch a mile. That would fit perfectly if I were to scale that out. Survey Pro Blunder Detection won't allow that. But is my 1,000 meters really 1,000, or is it 999.98? Something like that. So I've got scale and rotation, and it's when I enter a third point that I now have developed a plane, and I understand what my plane is looking like and the inherent risks of that. You can see up on my table that I've now developed residual error in the horizontal. I will never get 3 points to fit perfectly unless I'm in an ideal world, and we know we're not in an ideal world. So you can see I've begun to introduce some horizontal error, and as soon as I enter the fourth point into my project, I now introduce 3-dimensional error. I've got error in the vertical, 4 centimeters you can see on point number 3. I've got air in the horizontal as well in the millimetric range. And when I enter a fifth control point, you can see that I've got like bad vertical on point number 3, and I've got questionable vertical horizontal on point number 5. And in this very simplistic example, I turn those off, and now all of a sudden Survey Pro recomputes a best fit. In fact, I can have Survey Pro compute which points to turn off in the horizontal and vertical, and it will automatically do that for me. In this example, I used it manually, obviously, and you as a user ultimately have control. So here I have developed the best fit of 5 points within my control. I've developed a somewhat rubber sheeted horizontal and vertical control environment that I can work in. The points that I'm using are boundary to my project area. That means that any amount of error that I've got in these points will be interpolated to 0 at the center. So as I approach the center of my project area, theoretically, all of my error disappears. That indirectly infers that maybe my control point should be a lot further away from my project area to help me develop that plane, that vertical and horizontal dimensioning that I'm looking for. It might also indicate that I need to make sure that the quality of my control is pretty much the same. I better have, I should not have one point out there that I'm questionable about in one of the dimensions if I intend to hold that dimension horizontally or vertical in my calibration. So with this thought in mind, and the fact that I've told you to, in essence, use an inclined plane method, which is what this technology or this technique implies, before I leave it, let me say that this technique here requires the least amount of geodesy knowledge. Now, it would be nice if I knew that I was in a state plane zone to actually assign that within Survey Pro, but if I was doing a house lot type demo, that would disappear, and I would not see any error. And many surveyors around the world use this, we call it a one-step transformation, to calibrate to their job sites, and without any knowledge of GNSS, it works. So with that being said, I'm going to let Graham talk about calibrating to an inclined plane.
Thanks, Joe. So really what we're talking about here is the vertical component of the calibration. You remember in the little flow chart we showed you, it showed the vertical part clearly coming off and being handled differently from the horizontal part. So the example that Joe showed with the project area, it was really that top-down plan view, and hopefully you can picture in your mind for the horizontal calibration, it's really nothing more than a similarity transform. We translate, we rotate, and we potentially scale a tiny bit, one set of coordinates XY to another set of coordinates XY. The vertical is completely different though. Joe, you want to go next slide? So maybe you've seen this graphic before. I stole this from the NGS's website as a sort of an official source to describe the concept. But really what we're talking about in all of the previous examples where you saw the project area and the sort of top-down plane, and when you're thinking about the horizontal calibration, which again is that similarity transform, that is a calculation that's all about, that's a physical reality that's all about geometry. Right, measuring a latitude and longitude on an ellipsoid, running it through some map projection, applying a similarity transform to that to get it to fit to your local stuff. That's all about geometry. However, taking that height and turning it into the elevation, that's all about gravity. And unlike geometry, gravity is not regular. So if you look at the picture down there with the ocean, that little dashed line, that represents the so-called ellipsoid. That's the regular geometric surface that GPS is measuring in. And then the blue line represents the so-called geoid, which is a theoretical approximation of so-called mean sea level. And what's important about that is that that is, again, entirely influenced by gravity. Water will flow downhill from a higher gravity to a lower gravity. And the important part about this illustration I want you to picture is the fact that the dashed line for the ellipsoid is not parallel to any of those other lines representing different surfaces of gravity. And the lines representing different surfaces of gravity are also not parallel to each other. And again, because gravity is based on the actual distribution of masses within the Earth, which is more of an organic thing than a regular geometric thing, so you get these differing lines of potential gravity energy that will get water to flow downhill. So let's go to the next slide, and what I want you to picture on this slide is talk a little bit about the geoid. So as Joe said, it's always a good idea to use a geoid, and I advise that you always do a vertical calibration to correct for any bias between your local control and what the geoid has established as a benchmark for that area, because you're always going to see some difference in a bias between the two surfaces. So you want to select 1 or 2 vertical control points to constrain your adjustment to the shift. Calculating a tilt correction requires control points that are spaced very far apart, and in many cases, impractically far apart. Now, that doesn't mean that I'm showing you this picture here, not to suggest that you have to get control points on both sides of the nation here. What you're looking at in this plot here is actually a plot of the so-called deflection of the vertical across the United States, as an example. And you can see from the graph below, the most values fall between 8 arc seconds and -8 arc seconds. And there's a maximum of around 1 arc minute there, about 50 to 60 seconds is the maximum value that this tilt or this deflection of the vertical exists anywhere in the United States. So if you want to switch to the next graphic there, Joe. One more. There we go. Okay, so I'm trying to boil this down to a simple scenario. So imagine the picture before where we saw the dotted line of the ellipsoid representing that regular geometric surface and the sloped line of the geoid or the gravity surfaces, and there's some tilt in between those two lines. And the tilt in between those two lines, that's what a geodesist would call the deflection of the vertical. When you calculate an inclined plane vertical calibration, you are essentially picking a tiny slice of that deflection, assuming that one surface is parallel to the ground and the other surface represents one surface is the ellipsoid, the other straight surface is the representation of a little slice of the geoid in that area. And when you use your measurements to do that inclined plane transformation, you're essentially trying to calculate the deflection of the vertical. Well, here's the rub, here's the problem. Your GNSS receiver, worst case scenario at 3 sigma, being confident about the result, you've got about 3 centimeters of vertical random error. And if you look at the worst case scenario, if you think about on one end of your control point line, the error was all going up, and on the other end of the control point line, you got unlucky and all that error was going in the opposite direction. So from end to end, you might have 6 centimeters of, worst case scenario, vertical error. Well, you have to have those points separated by at least 400 meters before that 6 centimeters of error is even equal to the effect that you're trying to measure in the first place. So essentially, if your vertical control points are only 400 meters apart, your random measurement error is at least as noisy, if not noisier, than the actual thing you're trying to measure to. So in reality, if you're trying to do a nice tight vertical calibration inclined plane and get any better than the geoid can already approximate for you in terms of tilt compensation, then your control points need to be a few kilometers apart. So your random error is now an order of magnitude smaller than the thing that you're actually trying to measure. And that's rarely practical. People rarely do that. Yet, there's sort of a misbelief, in my opinion, that I always want to do a vertical calibration with as many control points as possible. And I don't believe in many cases that's true, especially in the continental US and in Canada, where for 30 years they've been spending copious quantities of our tax dollars doing tremendous science to measure the actual gravity field of the land. And if you use any of the modern geoids, they have a much better tilt correction, built into the Geoid model. So as long as you do the shift, as long as you do a calibration with 1 or 2 points to calculate the shift bias between the model and what your local benchmarks are, you will almost always get better results, allowing the Geoid model to account for the tilt between the surfaces as you spread away from that middle versus trying to do your own vertical calibration.
Thank you, Graham. We're getting short on time. So Joe Binder, if you could give display control over to Graham. I'd like him to just quickly step through what a demo calibration, maybe we have dealers on the phone or on the call that would like to see how to actually do it. You can do it on a desktop using the demo mode of Survey Pro. And if we can switch the screen display over to Graham, then he'll be able to show that.
Okay, can you guys see Survey Pro running here now?
I do not.
Okay, just a minute.
It does appear to have switched over.
Okay, stand by.
Yep. You had it there, Graham. There we go.
Okay, I've got it back. Okay, so using Survey Pro, I'm going to do a real quick demo here today. And full disclosure, I'm sitting in my home office and I do not have a GPS signal in my office. I'm going to be conducting this demo using the demo file that ships with Survey Pro. If you've never experimented with demo mode, you may notice that when I'm in GNSS, I can pick the so-called demo mode receiver. Is that showing up all right for you guys? It's kind of jumping here.
I don't see your screen at all. So I'm worried that others.
Mr. Binder there, are you seeing Survey Pro?
I am seeing Survey Pro.
Okay.
And there has been no input from anyone saying that they're not seeing it.
Well, my screen has a Survey Pro demo calibration - Graham Briggs up there. So don't.
Okay, I think the audience, Joe says the audience is actually.
Everyone is saying they're seeing it just fine.
Okay, cool. I will carry on.
Thank you, those who have chimed in. Thank you.
Okay, very good. So again, we're using the demo mode receiver, which actually uses a text file that you'll find in the Survey Pro program directory, and it just reads coordinates out of a simple ASCII text file, which also means that you can customize it to your own demos, which is a little bit outside the context of this call, but if you're interested to learn more about how the demo file works and how you can customize it to your region, to your specific location, maybe you have a cool background map you want to use with your demos, reach out to Joe or myself and we'll give you some instructions on that. So what I'm going to do here today is show a simple calibration. I'm going to start a brand new job. We'll go through the job creation wizard. I'm Canadian, so you'll have to forgive me. Working in meters here is what I understand a little bit better. We're going to do this in the simplest case where I'm starting a new job. I've got no coordinate system that is known. I do have a bunch of coordinates in an ASCII text file that someone gave me to import. So I'm going to go over here and I'm going to pick a text file and I'm going to choose a file for import. And I, of course, have the wrong folder. I had it all queued up. Stand by. There we go. I'm going to import some ground coordinates as if they had come from a total station survey from some time in the past. Meters, plane, we'll go ahead and finish. Quick look at the map shows us that we have a number of coordinates surrounding our...
Hey, Graham?
Mm-hmm.
I don't believe we are seeing your screen change here, though. That's
see, I think
that's
one of the issues. It's just the file screen still.
Okay, I'm going to go and try to share it slightly differently.
Oh, got a flash of it there.
We're seeing multiple screens there, so.
Okay, so now you see my whole. Now you see the whole thing, right?
Correct.
Let's try it one more time on Survey Pro. Can you see just Survey Pro?
Move your cursor there. Now I see your cursor moving. Yes.
Now I'm going to the survey menu. Can you see it on the survey menu?
Now we see you.
Yes.
Okay, good, good. Okay, well, if you didn't see
that
last...
Graham is a geodesist who is an expert at Survey Pro, and we will get him up to speed one of these days on webinars.
On webinar, yes, thank you. Okay, so if you missed that last part, all you really missed was I was creating a job and importing some points. So hopefully that's something that's somewhat familiar. At this point, I'm going to run through the calibration routine from the very beginning of Start Survey. So I'm going to hit the Start Survey button, and because I'm using the demo receiver, you guys see demo rover, demo base. I'm going to use demo network rover to make a connection to a fake NTRIP network. Again, this is all with the virtual demo mode. So here's that really important choice. I know that I've got ground coordinates that are not related to any projection and any datum, so I pick use ground calibration. I also have the choice optionally to use a geoid model. Always use a geoid model when you can. We'll use the latest, which is Geoid 18B for CONUS, and we'll accept that. So because I'm running through the Start Survey wizard as a network rover, it is waiting for the NTRIP network to broadcast the initial position and allow me to begin my survey. And again, in demo mode here, it's kind of simulating the real world. The broadcast comes from the NTRIP provider, every 10, 15 seconds, depending on the provider. So now when I hit next, my rover equipment is set, and it's asking me where is this base from? And again, because this was a no projection, no datum scenario, and I put my base out anywhere, or used an NTRIP network, which was in no way tied to the original survey, I'm just going to say that this is a new point for the job. And at this point, it's now prompting me to solve the calibration. Again, it's not that special 1 point scenario because I have a number of points that I came into the job with. So in order to get it done here, I have to occupy 2 points to create control for the resection. So let's go ahead and do that. I'll just go and use my map and pick this point here from my map and occupy that. And if I change my mind on if it's used for horizontal or used for vertical, I can change that condition here. Now it tells me, hey, I got to get 1 more to get control for the resection. So let's go over here and get point Lily. Okay, so now it's giving me the indication that I now have the minimum solution I need to solve that GNSS resection. I've got my base at a point in the job, and I've got my 2 resection points. And at this point, if I hit start now, I have that minimum solution that Joe talked about. So I don't have any check. I don't know for sure that this is any good. So best practice is we prompt you to occupy an additional control point. So let's go ahead and pick 1 more point. And again, we want to try to avoid having everything in a straight line. So we'll pick something over here to get a nice triangle. And when we occupy control point now, I want to point out up over here, right, because we now have the minimum required for a solution, over here we can show you how this next point is agreeing with the current solution. And you'll notice we have a nice tight agreement. And then that brings us to the final page, right, where we are shown that, hey, we have a good horizontal solution, it's showing us a green light. We have a good vertical solution. It doesn't have an RMS yet, but we can use the individual single points because we have a geoid to check it with the blunder detection routine. If I really wanted to, I could go ahead and add 1 more point right in here. Maybe let's pull that one out a little farther away. Right? Again, it's showing us the closures because we're adding on top of a minimum viable solution for the scenario. Now it's showing me green light in both horizontal and vertical. And when I hit finish, I am ready to survey. I want to demonstrate 1 more thing real quick that Joe mentioned called the blunder detection routine, because quite frankly, if you do your work well in the field, you will never see this routine. But I want you to know that it's there kind of protecting you. So what I'm going to do is I'm going to go to the job and I'm going to grab 1 of these points from my control collection that hasn't been surveyed on yet, and I'm going to edit it. And I am going to intentionally introduce about 10 centimeters of air in the northing and the easting just by changing this coordinate. And we'll leave the vertical for now just to keep it a simple example. Okay, so that was on point CBC3. As Joe mentioned, even after I've solved my calibration, maybe I've even collected a data point or 2, I can go back at any time and I can add additional control points to my calibration. Let's go ahead and add that point that we just edited, CBC3. We're going to add that as control. And then when we go back to projection and solve calibration, can you guys see the message that popped up?
Yes.
Blunder detection? Yes? Okay, excellent. Again, my screen's kind of going funny. So yes, detected blunders with the calibration. Do you want to automatically change the GNSS control points to remove the blunders? Well, let's say we don't know any better and we say, no, I don't want to do that. I think all my points are good. Okay, here's what I want you to notice is that you have, obviously the biggest residual is on here. And if I manually removed that and hit resolve, then hey, everything's good and green light again. But again, what the blunder detection is doing for you is it's running all the different combinations of unique solutions and checking it against all the other control points. And if it finds something that doesn't match, in this case, I'm going to turn CBC3 back on, right? And again, I'm getting this prompt. If I say yes, please do remove the blunders, you'll notice that it removed CBC3's horizontal. That was automatically deselected for me, but actually the vertical was good, so it automatically kept the vertical for me. So what the blunder detection routine is doing for you in the background, it checks essentially for systematic errors or so-called biases, right? Least squares requires that only random errors are included in the data set. If you have something like a bias, in this case, we kicked, the bulldozer ran over that pin and shifted it 10 centimeters in the ground from where it was supposed to be. The blunder detection routine will pick that up for you, and it will prompt you to get rid of the points that don't fit that so-called random error distribution, right? The points that stuck out as blunders, and it tries to detect that for you and remove it automatically from the solution.
Thank you, Graham. Joe, if you could come back to my screen, please. I'm hoping you can see my screen again.
Mm-hmm. Yep.
Great. So we're almost done, people. I know we're running a little long. I apologize for that. 4 points or more in my mind. We demonstrated that we can get away with 2 points with no redundancy, no check. 3 does provide horizontal redundancy, and we can rely on the Geoid model, as Graham explained. But really, if we want to hold the local control 4 points or more, one-step transformation is probably, not probably, it is the most common way of dealing with coordinates that have no datum, no projection associated with them. A 1-point, one-step transformation is appropriate for known projections, known datum coordinates. So we talked a couple of times about that, how it's still possible to solve the calibration even though you have selected a job with a defined projected system. And then finally, the instrument type that you're using, this AutoMagic stuff we talked about, whether I'm using a total station or a GNSS, Survey Pro manages that scale factor, manages rotations for me. The coordinate system sits at a higher level than the instrument as far as the hierarchy of these points. And so if I switch between the two, if I run the integrated survey where I have both GPS and total station at the same time, Survey Pro will manage that for me. And with that, I want to thank you for your attention. It's a difficult subject with a lot of nuances. I really want to appreciate and thank Graham for joining us today. I know he added a lot to the conversation. And we are not on a strict agenda. If you guys want to stay and ask questions, Joe Binder will be happy to chair those, and probably Graham will be the person answering them. Thank you very much.
So thank you both. Appreciate your time. And yes, we've got a question that's come in. Does a 1-point calibration measure points ground or grid?
So the answer to that is definitely ground. And if you look at the projection page, for example, on a 1-point calibration, once it's done, if you go back to the projection page, it will tell you that that distances are scaled for the ground at height X. Right, and that's essentially what you're talking about. When you're talking about, scaling to ground or grid, right? You're really talking about, is there map projection distortion, and how high above that map projection reference surface are you? And actually, maybe Joe, if I could go back to screen sharing, probably the easiest way, if I got a minute to answer, is, oops.
That's the screen you were talking about.
Yes, there you go. Sorry, right there, Joe. Yeah, that's perfect.
Me to go back here to Mr. Sass?
Yeah, sorry, go back to that screen if you can. So on that projection information screen, it tells you explicitly what height is being used to scale up to ground distances. In terms of the projection scale factor that is being used, we essentially set the projection scale factor at 1 point, whatever your height is, right? Where height is a function of what that gets set at. So the simple answer to your question is when you do any one of those 1 point calibrations, or for that matter, any of the calibrations in the ground, the default ground mode, the default ground calibration type, they're all designed to work at your current height or your current elevation above sea level.
So the next comment and question was, I always thought that 2 point vertical calibrations were bad. Is that wrong?
Well, yes and no, right? So again, think about what a vertical calibration is correcting for. A vertical calibration is correcting for two physical effects. Number one, your local elevation benchmarks and somebody else's definition of mean sea level might have a shift or a bias between them. And number two, actual gravity surface has a little bit of a tilt to it relative to the perfect geometric surface that GPS height is measured from. So you got two things to correct for. You got a shift and a tilt. Okay, my point is that you always need to correct for a shift. So you have to do a vertical calibration on at least 1 or 2 points to correct for the shift. My point is that with modern geoid models, they already have that tilt dialed in. So if you go ahead and do 3 or more points for your vertical calibration, you're essentially trying to measure the tilt better than the NGS's $100 million gravity program has been able to determine the tilt, right? Which is not impossible, but the whole point is that you got to think about what you're trying to measure. You're trying to measure a tilted surface that is tilted no more than 60 seconds, and typically no more than 8 seconds. So you're trying to measure a surface tilted at 8 seconds, and you're trying to do it with a GPS pole that's measuring 2 to 3 centimeter verticals, right? So
if you hold 2 points, though, aren't you then introducing this tilt? Shouldn't you?
No, because the way Survey Pro works in the vertical calibration is if you have 1 or 2 points, we only calculate a shift. We do not begin calculating tilt until you get to that 3rd point.
I think that was
because
critical to the question.
Yeah, definitely. With a 2 point calibration, you're still not getting tilt. You're just getting shift 1 plus shift 2 averaged together, right? So you're getting a better answer for your shift, but you haven't yet introduced tilt.
Yeah, I think that probably.
So again, my best practices for vertical calibration is 2 points in the vertical, and don't use any more. Don't allow it to calculate that tilt. Again, I mean, if you have super tight vertical control points and they're 3 or 4 or more kilometers apart across a large job site, then yes, you can achieve some additional benefit over top of the geoid. But I think most people, they go out and they've got one skanky benchmark over here and another one over there, and they're only a couple hundred meters apart, and they think, hey, more is better. But in many cases, you're actually introducing more tilt from your measurement error than the actual physical effect that you're trying to solve. So keep in mind that geoid models already have this tilt baked in, right? You always want to do that shift to calculate or to account for the bias in your local elevation to the geoid model mean sea level. There's always a bias there, but in my opinion, you're better off to use the tilts built into the geoid model than to try to do better with measurement on GPS control points. Again, especially, I mean, it's 2020 now, right? Like this would have been a different answer when I first started, working for Trimble and surveying and 20 years ago when we had Geoid 96, but with Geoid 18, it's good shape.
Right. Thank you again for your help here. Joe Binder, are there other questions?
Yes. So there was one more clarification on this, which is 2 points should just create a constant plane vertical adjustment, correct? And I believe that we kind of went through that. If there's more to that, Jeff, just let me know. Another one that did come in was someone was asking if you could show, run through doing a calibration using the mapping projection.
Yeah, certainly. Do you want to go back to screen share?
I'm doing so right now.
Okay. Okay, if I can show Survey Pro again. Can you see that, Survey Pro?
Yes.
Yes.
File mode now? Okay, so let's go ahead and do a new job. And really what I want to emphasize here is it's exactly the same workflow with the exception of you pick a mapping plane instead of we generate a default mapping plane appropriate for the site that you're standing on in the background.
Before you hit new, can you open the last job and show them where we use the oblique stereographic in the background?
Sure, so this is the job we just did. If I go to survey and projection, again, it tells me my calibration is solved. You know, back to the previous question, anytime you're in this default ground mode, we always quote at what specific height are we scaling ground distances. And then if you click on show details here, so here you'll see the first part is the properties of the calibration itself, right? What is its origin? Well, I was working in 5,000 coordinate set, so it's somewhere close to that. Here's that rotation and that scale. And as Joe said, you should be looking for something with 4 or 5 zeros or 4 or 5 nines, which is telling you that your control point is either matching the map projection in the mapping plane case, or your control points are matching the elevation we chose to scale that default map projection. And here's where that default map projection is. Okay, so the zone type is an oblique stereographic, and it has this really specific origin, latitude, and longitude. And that's because when you go into this default mode, you got to have a map projection somewhere. You cannot take latitude and longitudes on a curved surface of the ellipsoid and draw them on a flat piece of paper without using a map projection somewhere. Again, really the only difference between mapping plane mode and default ground mode is that in mapping plane mode, you pick the projection, and in default ground mode, we initialize this default projection. We give it an origin of whatever GPS coordinate you happen to hit first with your rover pole, and the offset coordinate, or the origin northing and easting, is whatever the control point coordinate was of that position that you hit for your first control point. And here's something to point out. You'll notice, so this scale here, this origin scale, this is the scale of that intermediate or that background default mapping plane. So you remember before Joe mentioned that if you've got a UTM projection, your origin scale is 0.9996, right? If you've got a state plane projection, your origin scale is typically 0.9999 something, 4 nines and something. It's typically less than 1, because most map projections are designed to kind of split the difference of the scale error across a very large area. So it's a little bit less than 1 in the middle, right at the center, somewhere out on the halfway to the edge, it'll be exactly 1, and then out towards the rest of the edges, it's slightly greater than 1. What you see here is that we have set the origin scale factor to be 10 parts per million. Okay, so you got 4 zeros plus 10, so there's your first 6 numbers, 0, 0, 0, 0, 1, 0. That's essentially 10 parts per million, which is the proper elevation scale for being about 66 meters above the ellipsoid surface, which is where we are in this example that I've got. So that really comes back to that other question too, is calibration operating on the ground? Yes, calibration is operating on the ground because we take your initial control point height and we use that to set a scale factor of the default projection that is at your height. And I know it doesn't look like much here because we're in Oregon and we're not very far above sea level down here in the valley, but these 10 parts per million, that comes from being 66 meters above ellipsoid height.
Okay, now solve the...
Okay, so what does it look like for mapping plane? Again, very, very similar. We're going to start a new job, right? We'll give it a different name, and we'll go through in our settings this time. So this time we're going to select a coordinate system to use, right? I'm going to pick a zone from the database, Oregon North, which is where I'm sitting right now. I'm going to have bring in some control, so I'm not going to bother entering the first point. We'll just go ahead and click finish. And now I'm going to import my control from a text file. This time I've got Oregon North coordinates, and they're going to go on the point layer, and I'm all finished up with that. So if I have a quick look at the points, right, I see, and we'll kind of collapse code and description here. Okay, so I see northing and eastings are like 100,000, 2.3 million, you know, really big coordinates. Those are typical of mapping plane. If I clicked on any one of these, one thing that you'll notice right away is that, look, it's showing me a geodetic coordinate. And that's because anytime you have the mapping plane solved, you can take a source grid and convert it to geodetic in the same way you can take a measured geodetic and convert it back to grid. Okay, so now that I have these coordinates in my file, let's go out and do a typical survey. And we're going to do the example here where I'm working on mapping plane. So maybe if this was an NTRIP network, or maybe if I could set my base right up on one of my known monuments in that coordinate system, I could proceed directly to data collection like Joe said, right? If I've got a mapping plane, so now scale and orientation is known, all I need to do is set my point of beginning, and anytime I put my base on a known point of beginning, I'm ready to go. In this example, we're going to show you where you're obliged to calibrate, or the example of I got to set my base on top of that hill because it is, you know, secure location. So we're going to start from a base receiver, and we're going to assume that we're putting that on an unknown new location. So I connect to my base, it gets its autonomous position. It uses that autonomous position to, I've got a point that's catching it up here. So we're gonna override that. We're gonna set it up on a brand new base. And what you're actually seeing here is Survey Pro has a function when you are in the mapping plane and you set your base up on a position, if that autonomous position is close enough to any real position, we try to prompt you or warn you, hey, are you sure you're not on this point that's right in that same neighborhood? In this case, I'm going to override that, and I'm going to force it to assume that that's a brand new point in the job. So I go ahead and finish that. I move on to my rover. I wait at the rover for the base to be broadcast, and then I click next. All right, now you will notice that we are being prompted in the same way we were before to solve the calibration. But you'll notice in the case before, where it was a default ground mode, where the orientation is unknown, we needed 2 points in that case because we needed to know where was the point of beginning and what is the orientation. Here we know orientation and scale from the definition of the mapping plane, so all we're trying to correct for is the point of beginning, and you'll notice it's prompting me to occupy only one additional control point to create control for the resection, and that's because only one point is required for a minimum solution in the mapping plane case. Workflow is exactly the same. I'm going to occupy control. Let's pick something central here like Lily. And I will collect this control. Okay, so again, now it advances to the next page where it tells me I have enough control for a minimum solution, but best practice should be to occupy one additional control. So I'm going to do that now. We'll grab this point over here, Craig. Okay, and again, it's coming in very tight. We'll go ahead and accept that. Now again, we're not able to run, we're not able to run the vertical blunder detection, but we did run the horizontal blunder detection in the background. That's how you know that, because you have a green light. And if we looked at the details of what this calibration is about to solve, okay, I want you to observe here, shift north and shift east, and the rotation is infinitesimal. and the scale factor is 1 part per million, so also, you know, nearly infinitesimal.
And
So this,
the shift north and the shift east is directly related to that rotation factor.
actually, no, I was going to say so remember, we're in a mapping plane case here, and I was using this special demo mode where I was kind of feeding it in canned coordinates. Well, the coordinates that I feed into it happen to be, I took the original control coordinates, so the same, the grid points that I imported, I took those points and I shifted them by 10 meters north and 10 meters east, and then I generated geodetic coordinates from them, and that's what I'm using for demo mode, essentially to simulate putting a GPS receiver on an autonomous position and starting from a here position, right? You know, 10 meters is worst case scenario, and especially in these days with so many birds, with WASP, you know, running for you, you know, maybe even RTX in the background if you've got a subscription for that, you're typically going to do much better than 10 meters. I took the worst case scenario, I took the original control coordinates, and I shifted them by 10 meters north and east to generate this demo file for the measurements. So what you're seeing here is a shift of, and again, it's not quite perfect because there's a little bit of rubber sheeting, and even at this scale, you know, the fact that this is 10.001 and not exactly 10, right, is you're kind of seeing that effect of the grain of the map projection, the scale distortions of the map projection, right? This is a Lambert projection, so moving east-west versus north-south, right? You've got a little bit of scale difference. And actually in this case, the reason you see any rotation at all is what you're actually seeing is the meridian convergence between the autonomous GPS position and the actual proper grid values, right? So you're essentially seeing you're seeing a tiny little bit of meridian convergence when you, which is essentially the, you know, if you did a sunshot at the real position and the sunshot at where the autonomous GPS position was, you're going to see that tiny little, you know, tenths of an arc second in there as meridian convergence.
Okay, so finish the calibration, please.
Yeah, so that's the info on it. So yeah, now all I need to do is finish, and I'm collecting data. So the workflow is exactly the same.
The parameters that show that the Lambert parallel is being used and not the
yes, definitely
stereographic. So you
yeah, so let's actually, that's a good point, Joe. Yeah, let's go to the projection information page. So now I'm in mapping plane mode as opposed to default calibration mode. The calibration is solved. You'll notice it doesn't give a height here anymore, and that's because we're no longer working in ground distances. We've calibrated to, and we've provided control coordinates that were in grid distances. So let's go ahead and show the details on that. So again, we see the same sort of details for the calibration. That's what's being applied, and we've got a vertical adjustment with no no slopes, no tilts, just the separation value, and that's the 10 that I shifted it by. And actually, the reason you're seeing almost a centimeter here is I prepared these control coordinates many years ago using Geoid 09, and we're applying a slightly different Geoid here, so we get a slightly different answer. But to Joe's question, here's where you see the zone or the map projection that's being used underneath this calibration. Remember, calibration is just a similarity transform. Shift, scale, and rotate one set of grid or XY to another set of XY. In both cases, one set of XY is the control coordinates you provide, and the other set of XY is the measurements through the GPS onto whatever mapping plane is in play. And then really the only difference between mapping plane mode and default calibration mode is that in mapping plane mode, the mapping plane that's being used is the one you picked from the database. And in default calibration mode, the mapping plane that is being used is one that we cooked up in the background based on the origin of your first control point collection.
In this example, oblique stereographic versus the Lambert conformal that you see here.
That's correct.
Thank you very much.
Now, for what it's worth, I'm just going to sort of show this to the audience because I know the question of scale comes up a lot. And as Joe said, you know, we take care of it automatically for you in many scenarios. But, you know, this user's question was, hey, how do I do this calibration in the mapping plane? So now we've done that.
So
now yep, go ahead.
Graham, I was going to say that the gentleman also was asking, so if we have a state plane coordinate at ground on a set plane, should we still use mapping plane?
A state
I'm
plane
sorry.
coordinate on ground.
I'm sorry, let me reread that here. So if we have a state plane coordinate at ground on a set of plans, should we still use mapping plane?
Okay, well, that's a great question. And that, quite frankly, that I think is its own webinar, right? So, but let me show you real quick the way that I recommend handling that situation. So as Joe mentioned, if you go to job settings, right, and you've got the scale factor page, and right now we're using automatic mapping plane on Oregon North, which means that if you measure 100 meters with your total station on the ground, we're going to turn it into 99.96 on the grid, or 9.8 or 1.0, depending on your height. But you know what I'm saying? Like when mapping plane scaling is applied, you're going to measure 100 meters on the ground, and it's typically going to be a little bit less on the grid. And that's all taken care of automatically, and the scale factors are correct and calculated for you. But it's always difficult to, when you're trying to stake out a house and the frost footing has to be 5 feet from the property line. You don't want to have to turn that into 4.998 or something on your grid reference. So in Survey Pro, we have this mode called ground scale factor, and it's only a mode that is appropriate in mapping plane, because of course, when you're in the other GNSS mode, when you're in default calibration, everything is working on the ground for you, right? We're scaling everything at your control point's elevation. But on the mapping plane, you're down on that grid. So to do what you want to accomplish, go to settings, survey scale factor, right? And hit setup scale, and change it to automatic mapping plane ground. Right, the default when you pick a mapping plane is to put you in automatic mapping plane grid, where horizontal distances are scaled using the grid factor at each setup and the sea level correction for each shot. Right, if you go to use this mode, automatic mapping plane on the ground, we essentially take that reference grid and we scale it up to 1-to-1 on the ground using a location in your project and that location's height that you choose. So let's see what that looks like. So here we are again. Anytime you talk about scaling a grid to a ground, there's those two scale factors. So the amount of scale that you're applying depends on where horizontally you are in the grid. That will be your projection factor, and how high that point is above the ellipsoid surface. That's your elevation factor. So let's go ahead and say, hey, this is a pretty big site. Actually, these control points, go all the way across our county. But in reality, I'm just working over here on this little part of the site, right? We're laying in a parking lot, on this lot here. So maybe somewhere around P7 is a nice centroid of my project area at a good representative elevation. So I'm going to pick P7 as the origin point that I want to scale at. And then I go here and I say, what do I want the scaled coordinate of P7 to be? This routine allows you to apply an offset. And the reason we do that is that if you just scaled around P7, right, P7 would still be at like 102,000, 2.5 million. Its coordinate would be completely unchanged. And the coordinate right next to it would be almost unchanged, and a coordinate a kilometer away would be a little bit more changed. But with the scale factor applied around that point, right, points will change very slowly. And there's always a danger that you don't recognize, am I working in ground or am I working in grid? So what we do is we allow you to apply essentially a false offset, whatever you want that coordinate to be in your scaled system, dial it in here. 5,000 is the default, but if I want it to be 4,000, 6,000 for whatever reason, I'll just dial that in here. Now let's go apply that coordinate system, and we have just readjusted everything, scaled it up to ground for the reference height of 55.609, which was the height of the point that we've chosen. So what does that mean? Well, let's go look at the points. Okay, so first of all, you'll notice right away that my points are no longer 5,000, or pardon me, my points are no longer 102,000, 2.5 million. They're all in sort of a 5,000 range. And if I actually found the reference point that we picked, which is right here, P7, you'll see it's exactly at 4,000, 6,000. However, if I go to look at the properties of any one of these points, okay, it's giving me its current ground location because I've applied this ground scaling. It's also giving me the proper mapping plane location of this point, right? So it's showing me the mapping plane location that's underneath this scaled location. And, you know, maybe I screwed that up. Maybe I'm like, wait a minute, P7 is on the top of a ridge and it's 100 meters higher than the rest of my project area. I really want to set it up with a better scale reference. Well, I can just go in here and change this. Let's pick a different point. You know, maybe let's scale it on Matt's house, right? And, you know, I didn't really want 4,000. I wanted it at 5,000, 5,000. So I can go ahead and apply that. And I can look back at the points. And let's go back to P7, which was here. So it's a little bit different now because it's no longer the origin. But if you have a photographic memory, you might recognize this coordinate because it's the exact same proper mapping plane coordinate underneath. And that's really one of the beauties of the mapping plane ground mode that we have. So let's say, for sake of argument, that this was the reference height and this is where I wanted it to be scaled for ground. But then I wanted to switch back to working on the grid for a while. Well, I'll just come up here and switch it back to the grid. And when I hit this button, everything has been readjusted. And now if I look at, you know, let's pick on Matt, which was our new origin, right? Matt's house is at 95,547, 2.284 million as a coordinate. And that's its proper Oregon state plane coordinate. I can now go to the settings. I can change that to reapply my ground system. And because I've already applied one, and let's just reset the last one we used because I'm switching back and forth. Now let's go have a look at Matt's house. Right, it's at 5,000, 5,000 again. And I can switch back and forth. Oh, it's got a little scale bias there, but I can switch back and forth between these two coordinate systems. I can pick a different scale reference. I can take it higher. I can take it lower. And it's a transformation that is kind of exact. And what I like so much about it is that it preserves the true mapping plane coordinates underneath, but it allows you to work in a ground scaled system. So when you measure 100 on your total station, it's 100 when you inverse it on the grid. But underneath, it's still calculating in the exact proper mapping plane. So, and it allows you to switch back and forth.
This is exactly the section of the program that I warned people against using. And you can see that it gets complex very quickly, and you better understand exactly the selections you're making. I would not have gone into those pages had Graham not been here, but Graham is obviously expert on this topic, so thank you for that extra bit of information. We have
I would definitely support, sorry Joe, but I would definitely support your disclaimer. It is important to understand what, you know, physical effects that you're correcting for, and how that automatic ground mode versus being in, you know, again, the default behavior is when you pick a mapping plane, you're in grid mode and we apply grid scaling, which Survey Pro is calculating for you based on each setup, right? You really do want to understand, you know, what you're doing if you apply a ground scale to that mapping plane mode. I definitely like to show that routine off because I'm pretty proud of it. And again, it is a little bit more advanced, but if you understand what you're doing and how the height and the location on the mapping plane impacts scale, it is a very powerful way to toggle from, you know, I got mapping plane control, but I got to lay out the house that has a 100-meter wall or 100-foot walls or whatever.
So we have consumed 5 extra minutes that we shouldn't have. I think if there are more questions, they can be sent to either Joe Binder or myself, and we will manage them offline. I'll turn it back to Joe Binder now.
Well, again, thank you both. Thank you all for your participation. This will be posted on our YouTube page in a day or so, as well as on our support page. And Joe Sass is Joe_Sass at SpectraPrecision.com, and myself, Joe_Binder at SpectraPrecision.com, should you have any further questions. Again, thank you and have a great afternoon. Bye-bye.
Thank you all. Bye-bye.
Thank you.